Hi, everyone. Today we're going to begin Unit 8, States of Matter. Now, even though the unit's called States of Matter, we're going to focus primarily on gases. Gases are actually going to be the most unique and the most different thing that we will look at as compared to solids and liquids. So, gases are affected by pressure, volume, temperature, and other factors that don't really have much of an impact on solids and liquids other than going through a phase change. In our conversation about gases, it's important to establish some foundational knowledge. So we're going to talk about that in terms of kinetic molecular theory. As you can see on your screen, based on kinetic molecular theory, the first one, gases are composed of large numbers of particles that behave kind of like hard spherical objects in a state of constant and random motion. I told my students in class that it's almost like billiard balls or pool balls on a billiards table that are bouncing off the sides of the table and each other. And if you've ever seen me play pool, then you'll know that they are definitely in constant and somewhat random motion. The second thing is that these particles tend to move in straight lines unless they collide with other particles, very similar to the way those pool balls would move around on a pool table. So they're going to collide with other balls on the table, or in this case, other molecules or atoms, and the walls of the container that they're confined to. Third, these particles are smaller than the distance between them. So the relative sizes of the molecules and atoms that we're going to talk about as we discuss gases are incredibly small compared to the containers they are in. So that allows for a lot of random and constant motion without ever colliding with anything else, whether it's the side of the container or another molecule or atom. The next couple of things that I want to mention are, based on kinetic molecular theory, there is essentially no force of attraction between gas particles or between the particles and the walls of their container. Now, we're going to find that that isn't 100% true, but for the calculations that we're going to do for this class, we're free to work under that assumption. Number 5, collisions between gas particles or collisions between gas particles and the side of their container are going to be elastic, which means that they're not going to lose any energy when they collide. Now, again, this isn't 100% true, but for the purpose of our calculations, we're going to be able to make that assumption. None of the energy that a gas particle has will be lost through a collision with either another particle or the side of the container. And finally, the average kinetic energy of a collection of gas particles is going to be based on their temperature. We're going to learn that the higher the temperature is, the higher the kinetic energy of those molecules. So there are a few basic points that I want to bring your attention to when we talk about gases. Some of this is extremely critical to remember when we go about and start looking at some of our gas law problems. So the first of which is temperature absolutely must be reported in Kelvin when you do your gas law calculations. Now, think about this for a second. Our Celsius scale has negative temperatures. Well, if we tried to use some of those negative temperatures in our calculation for pressure volume, we would end up with negative values for pressure and volume. So a way to fix that and to avoid the use of negative temperatures and thus the potential for negative pressure or volume, we're going to use temperature based on an absolute scale where 0, the lowest achievable theoretical temperature, known as absolute 0, is our lowest point. And then any temperature that we're able to record is going to be above that based on that relative absolute 0 value. Think about it this way. If we look at the boiling point of water as 100 degrees Celsius, in our Kelvin scale, based on this formula, Kelvin equals Celsius plus 273.15, our equivalent Kelvin temperature is going to be 373.15 Kelvin. Notice that Kelvin scale does not use a degree symbol. Well, similarly, if we were to look at the freezing point of water, which is 0 degrees Celsius, we would find that that has a Kelvin temperature of 273.15 Kelvin. Now, if we were to go down to the absolute lowest achievable temperature of 0 Kelvin, and there's debate about whether that's actually the lowest possible temperature or not, and there are some papers that are being published that suggest that it may not be. Please know that for our purpose, it's going to be completely fine to assume that absolute 0 or 0 Kelvin is our lowest possible temperature. So working backwards in this case, that would make that temperature on the Celsius scale negative 273.15 degrees Celsius. That temperature, as it says down here, is known as absolute 0. Now, with pressure, there are several different pressures that we can use. Pressure is going to be measured in either kPa, which stands for kilopascals, ATM, which stands for atmospheres, mmHg, which stands for millimeters of mercury, or torr, which measures the same exact pressure as millimeters of mercury, but acknowledges the contributions of one physicist. So they gave that 760 mmHg a special name, but we are going to use them interchangeably. Now, where the millimeters of mercury comes in is if you were to look at a barometer, the closed end, and an open end open to the atmosphere, and you had mercury in this barometer, you were to draw a line across, the atmosphere would be pushing down, and the difference between the left and right side of that barometer would be equal to 760 millimeters, or the atmospheric pressure at sea level. Now, we're not often going to be using millimeters of mercury, but it is very much used in other applications. So it's important that we at least see it, and we'll see it in some problems, and we may need to even convert to or from millimeters of mercury depending on the problem. The next term that you see on this list is standard temperature and pressure. Standard temperature and pressure is just a quick way of conveying a temperature and a pressure value in a problem. Sometimes you'll see it shorthanded as at STP. So when you have a scenario and it tells you that the gas is at STP, that's a short way of telling you it's at 0 degrees Celsius or 273.15 Kelvin and a pressure of 1 ATM or 760 mmHg. Okay, before we move on and start looking at some equations and some problems, I wanted to just quickly clarify for you the difference between a real gas and an ideal gas. We are going to be working under the assumption that our gases behave ideally. However, it's important for you to understand that in reality, our calculations might be slightly off from what is actually happening because of two things. Number one is when you have high pressure and low temperature situations, the gas molecules tend to move slower and they are allowed to attract each other somewhat. And as a result, they can kind of deviate a little bit from what our calculations would predict. So as you can see in number one, it says at high pressure and low temperature, a gas's kinetic energy can be insufficient to overcome attractive forces between molecules, which does become significant if we were doing very precise calculations. Now, we're not going to have that problem because our calculations are not going to be that exact. And second, when we talk about the volume of a gas, we ignore the fact that the molecules and atoms have a volume themselves. We ignore that and we just use the volume of the container that they are confined to when we refer to volume. Again, that's going to be perfectly acceptable for any of the calculations that we're going to do in here. In fact, it's perfectly acceptable for most of the calculations that you're going to see next year if you go on to take AP chemistry or even your freshman year of college if you were to end up taking chemistry in higher levels. So today we're going to look at 3 different laws. The first of which is called Boyle's law. And Boyle's law talks about the relationship between pressure and volume for gases. Now, in order to isolate the relationship between pressure and volume, we're going to keep temperature constant. So in all of our Boyle's law problems, we're not going to mention any changes in temperature. So if you look, the equation P1 V1 equals P2 V2 talks about initial and final conditions. So if you imagine the side that we identify as 1, those are kind of our initial conditions. The opposite side here are our final conditions. So we're going to work under 2 premises. Number 1, as the pressure of a fixed amount of gas at constant temperature increases, the volume is going to decrease. You can almost think of this as like a balloon. If I were to squeeze a balloon, so if I were to increase the pressure on a balloon, I'm going to decrease the volume of gas, or the volume that that gas is occupying, by squeezing the balloon. So this is known as an inverse relationship. As I increase pressure, volume is going to decrease. If we were to represent the relationship between pressure and volume using a graph, we would see that at high pressure, our volume is going to be kept low, and at low pressure, our gas would be allowed to expand, so the volume would end up being higher. This is an inverse relationship between pressure and volume. So we're going to get a curved line that sort of looks like this. Now, let's take a look at an example problem that uses Boyle's law. When you're completing these problems, it's very important that you write down your givens. Often the problems are going to present information to you that's not in the order that you need to use them. So it's really important that you kind of follow along with what the problem is giving you and identify each variable as you learn. I like to start off by writing the variables that I'm going to identify on the left side, and then I fill them in as I read through the problem. So in this problem, it says, in a thermonuclear device, the pressure of 0.05 liters of gas within the bomb casing reaches a pressure of 4.0 times 10 to the 6th. So we can go ahead and write in our initial pressure, 4.0 times 10 to the 6th ATM, and our initial volume, 0.050 liters. The problem goes on to say, when the bomb casing is destroyed by the explosion and the gas is released into the atmosphere, it reaches atmospheric pressure, standard atmospheric pressure of 1.00 ATM. We can plug in our 1.00 ATM value here. And in this case, we're going to solve for our new volume. Now, we start off with our Boyle's law equation, pressure 1, volume 1 equals pressure 2, volume 2. And we're solving for volume 2. So in this case, we're going to divide by pressure 2 on both sides. So we'll wind up with an equation that looks like this. Volume 2 equals pressure 1, volume 1 divided by pressure 2. Once you rearrange your equation, now you can go ahead and substitute the values from the givens on the left side into that equation. Volume 2 equals my pressure 1, which is 4.0 times 10 to the 6th ATM. I'm going to multiply that by my volume 1, which is 0.05 liters. And I'm going to, in this case, divide by my pressure 2, which is 1.00 ATM. Now, think about this for a second. Before we get our answer, I want you to think about the relationship between pressure and volume. According to Boyle's law, it's inverse, meaning as pressure goes up, volume goes down. Or in this case, pressure is going down, so from 4.0 times 10 to the 6th ATM all the way down to 1 ATM. So if pressure goes down, volume should go up. So try and predict before you go and type in your values, whether the volume will end up higher or lower. So if pressure is coming down, in this case, our volume should be higher. So now I can type this into our calculator. So we have 4.0 times 10 to the 6th. So that's 4, 1, 2, 3, 4, 5, 6 zeros times 0.05 divided by 1. And I get an answer here of 200,000. So my volume 2 is going to equal 200,000. And in this case, we're using units of liters. If you've done the problem correctly, and if you've set everything up correctly, your units should confirm that. So in this case, ATM on top and bottom will drop out, and I'm left with units of liters, which is what I expected. Now let's take a look at our second law, which is called Charles's law. This law examines the relationship between the volume and the temperature of a gas, this time keeping pressure constant. So if we take a look at our relationship here, it says as the temperature of a fixed amount of gas. That means all of these are closed systems where we're not increasing the number of molecules of gas or decreasing the number of molecules. And the other part that we're able to do in this case is maintain a constant pressure. So imagine something like an accordion bottle, where in order to maintain the pressure inside the bottle is able to expand or contract. So in this problem, we see a direct relationship, meaning as volume increases, temperature increases. The easiest way to think about this is imagine heating something up. The volume starts to expand. If you had a plastic water bottle that you left in your car and the car heated in the sun's light, you would see that plastic water bottle kind of expand. And the reason for that is the gas that's trapped inside, especially if all of the water has been emptied out, the gas that's trapped inside tries to push against the sides of that container. So we will find out that the relationship between volume and temperature is direct, meaning if we were to graph this relationship at high temperature, we would also see high volume. So our graph would look like this. Let's take a look at an example problem of Charles's law. So if we take a look at this problem, remember first that we're going to write down our givens on the side. So if it's a Charles's law problem, we're looking at changes in volume and temperature only. So it says a man heats a balloon in an oven, and I just put a note there that heating a balloon in an oven is probably not a great idea because the balloon could even melt and destroy your oven. But if the balloon initially has a volume of 0.400 liters and a temperature of 20 degrees Celsius, so we're going to put that here. What will the volume of the balloon be? So we're looking for volume 2 after it heats to a temperature of 250 degrees Celsius. Now, with my in-person students, I trick them and I didn't remind them of the fact that in order to do this problem, before you can really begin, you need to convert your Celsius temperatures into Kelvin. Remember, we can never use Celsius temperatures in our gas law problems. We're always going to convert that temperature into Kelvin. So not going to play the same trick on you. Instead, we're just going to add our 273.15 to each of our temperatures to see what we get. So in the case of the first one, we get 20 plus 273.15, which is our conversion to Kelvin. So we get a temperature of 293.15. And for our second temperature, we have 250 plus 273.15. And in this case, we're going to get a temperature of 523.2 Kelvin. In this case, we couldn't get the 0.15 because here we had 2 decimal places, but here we had just 1 decimal place. So based on our rules of significant figures, we're limited to just writing 2 here. Okay, looking at our equation, we have volume 1 over temperature 1 equals volume 2 over temperature 2. We're solving for volume 2. So we want to cross multiply here. So we're going to get volume 2 equals volume 1 times temperature 2 divided by temperature 1. Believe it or not, most students that don't get this problem correct have a problem solving for the correct variable and rearranging the equation. So always remember, you can cross multiply, get your equation, and then solve by dividing out and separating and isolating, in this case, the volume 2. So now typing this into or inserting our values before we type it in, we have our volume 1, which in this case is 0.400 liters. We have our temperature 2. So we're going to multiply that by 523.2 Kelvin. We're going to divide by temperature 1, which is 293.15 Kelvin. Okay, once again, the relationship here, if we're trying to predict, is a direct one, meaning if our temperature goes up, which it does, it goes from 293 up to 523, then our volume should also go up. So when we get our final answer for volume, it better be higher than 0.4 liters. So let's type this into a calculator. So we have 0.4 times 523.2 divided by 293.15. So we get, in this case, a volume 2, which is in fact higher, 0.71. Looks like we have about 3 significant figures, so 0.714 liters. This is our final answer. Notice how nicely our units will work out. So Kelvin on top and Kelvin on the bottom are going to cancel each other out. Let's take a look at our third gas law. So the Lew Shack Law, based on 2 scientists, deals with the relationship between pressure and temperature. Notice that in this law, we're holding volume constant. So sometimes when you're doing a problem with Lew Shack's law, you might see a rigid metal container. And that's the problem's way of telling you that the volume is not changing. So a rigid metal container means you're at constant volume. So let's take a look at this problem. It says, as the temperature of a fixed amount of gas, just like we've seen before, at constant volume increases. So in this case, because temperature increasing causes pressure to also increase, we have another direct relationship. So just like we saw with Charles's law, we're going to have a graph that's a straight line going up to the right. Let's take a look at an example problem. So in this problem, it says, determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 to 30 degrees Celsius. So we have pressure 1, temperature 1, pressure 2, and temperature 2. Our initial pressure is 1.00 atm. That part's up here. Our initial and final temperatures are 20 degrees Celsius and 30 degrees Celsius respectively. So we're going to begin by converting our temperatures into Kelvin temperatures. So notice we have 1 decimal place. This is going to be plus 273.15 for a total of 293.2 Kelvin. And then 30 degrees Celsius, we're going to do the same thing here, add 273.15, and we'll get a Kelvin temperature that is equal to 303.2 Kelvin. This problem, Our second pressure is our unknown. So we're going to be solving for pressure 2. So we're going to have pressure 2 is equal to pressure 1 times temperature 2 divided by temperature 1. When we substitute in our values, we're going to have pressure 1, which is 1 atm, times our temperature 2, which is 303.2 Kelvin, divided by our temperature 1, which is 293.2 Kelvin. Typing all of this into our calculator, so 1 times 303.2, that's going to be 303.2, divided by 293.2. Now, before I press enter, think about what happened. We had our temperature go up. Because it's a direct relationship, we should also see our pressure go up. So our answer should be greater than 1. In fact, we wind up in this case with our pressure going up to 1.03 atm. Now, some of you are saying, big deal, it only went up by 0.03 atm, which is true, but remember, we only went up by 10 degrees Celsius, so that's not a significant temperature change. So it's only going to be a small increase in pressure. Okay, at this point, what I'm asking you to do is to try the highlighted problems on the gas laws homework. You can find this in the lesson 1 folder on Schoology. If you have any questions, please let me know by message, Schoology message, or by email, or stop by office hours. Thanks, everyone. Have a great week.